Welcome, friends. Now we're going to talk about tangent planes. So the first thing we're going to think about is going back to Calc 1. What does the derivative tell us in Calc 1? So in regular calculus, the derivative helps us define that tangent line to the graph of any differentiable function at a point, right? So the derivative is basically telling us the slope of the tangent line at a point. So what does the gradient do? We spent a long time in the videos before this talking about gradients. The gradient defines the tangent plane to the level surface. All right, and what does that mean? The tangent plane to some level surface, some function at some c value of a differentiable function f at a given point p, as long as the gradient's not zero, is going to be the plane passing through that point and normal or perpendicular to the gradient at that point. So basically, we did an example before where we found a tangent line to a level curve and we went perpendicular to the gradient. So in this case, we're going to go perpendicular to that gradient, but we're going to be finding a plane, not just a tangent line. So the normal line to this surface at the point is the line through the point P naught, which is parallel to the gradient of that multivariable function evaluated at P naught. And we can find both the tangent plane and the normal line using these formulas that you now see in front of you. So the tangent plane to a function at a point is the partial of x evaluated at that point, x minus the x value from the point, partial of y of the function evaluated at the point times y minus that y naught, and similarly partial of z at that point, and then z minus z naught equal to 0. And then the normal line is parametrized by the following x, y, and z. We take the x naught, y naught, z naught from the point, and then we have the partial of f at the point, partial of y at the point, partial of z at the point. We add all of those partials multiplied with t. So let's do an example of finding a tangent plane. For this example, we're going to find both the tangent plane and the normal line of this level surface. X squared plus y squared plus z minus 9 equals 0. And we're going to do this at the point P naught, which is the ordered triple 1, 2, 4. All right, so what is the shape of this level surface? And hopefully you recognize, going back to the beginning of our semester, that this is a circular paraboloid. All right, so we've got two things to do here. We have to find the tangent plane and the normal line. So we're going to start with the tangent plane. And the tangent plane is the plane through this point, the plane passing through the point, which is perpendicular to the gradient of f at the point. So the first thing we need to do, first step here, is going to find the gradient of f at my point 1, 2, 4. And in order for us to write the gradient, we need the partial of the function with respect to x, partial with respect to y, and then partial with respect to z, and each will respectively go with their I, j, and k. So partial of my function with respect to x is 2x. So I've got 2xi. Partial with respect to y is 2y. So I have 2yj. And the partial with respect to z is 1. So I have 1k. Of course, I need to evaluate this at the ordered triple 1, 2, 4. So 2 times 1, I, plus 2 times 2, j, plus k. My gradient is 2i plus 4j plus k. Got all my little vector notations in there. All right, so now that we know the gradient at that point, we can use these partials at each point, 2, 4, and 1, to tell me what the tangent plane is. So the second step, we have our tangent plane, and by definition, I'm going to write that out just to reiterate. So I have the partial of the function with respect to x at the point, and then we'll have x minus x naught, partial with respect to y minus y naught, plus the partial with respect to z minus z naught, and of course that's equal to 0. So I have 2 x minus the x value from my point is 1, plus 4 y minus the y value from my point is 2, and then plus 1 z minus my z value 4. And we can simplify this. I have 2x minus 2 plus 4y minus 8 plus z minus 4, which gives me 2x plus 4y plus z, and that would have been negative 14 on that, on the left side, so that'll be positive 14 on the right. So that's the equation of my tangent plane. And then we also need to write the equation of the normal line. So we write the normal line in parametric form. My formula is x equals x naught plus that partial with respect to x at the point times t, y equals y naught plus the partial with respect to y at the point times t, and z equals z naught plus the partial with respect to z at the point times t. So we have x equals, my x value given was 1, and then I'll have plus my partial with respect to x was 2, so I've got 2t. I've got y equals, the given y was 2 plus, I now have 4t, and z, I was given a 4 plus, I have 1t. You don't need that 1 there in front of the t for z, but I like to write it. So visually, what are these, what's this plane and these parametrized lines, what are they showing us? I'm going to pull in a picture. So here we have our circular paraboloid, and here's my point, 1, 2, 4. So there's my point on the surface. So the plane, the tangent plane, looks like this sheet of paper, and then the normal line extends out from that plane, and the normal line is perpendicular to the surface at that point. All right, so that's how we find a tangent plane to a surface, as well as the normal line to the surface at a specific point.